This is store width. It's our implementation of the store using the width notation. So we have the parser that looks the usual way for the parser, covering all our forms. We've got an interp and we're using width for the recursive calls. And we're not using any plate boxes to implement our own boxes. So that has the good effect that it means we're understanding store on its own terms. It also has a good effect in terms of testing. And let me show you what I mean. So we can try out interp on some simple expressions like parse of box 0. We need to do that now with an empty environment and an empty store. And what do we get back? As we would expect, we get a box back at location 1, and in the store it says location 1 has num_b0. We can write another example. We can wrap this with an unbox. So that's a way we can test unbox is by also having a box expression in our program, and so we get num_b0 out. But that's not the only way that we could test unbox. We could say unbox on x as the whole program, and if we just ran this right now, we would get undefined variable x. But I can change the empty environment to be an extended environment, where I bind x to be, let's give ourselves some more room. I bind x to be a box that's allocated address 1, at address 1. So now, if I were to run this program, then x would actually have a value because it would be found in this store. I've kind of jumped into the middle of a program evaluation by setting up an extended environment. It's not going to work though if I'm referring to location 1 and location 1 is not allocated. So let's also override the store to say that we're going to have a cell at address 1 that contains the number 6. So I can run this example now. It's as if I'm in the middle of a program computation. X will have a value as box v1. When we look in box v1, we will get the result 6 out. And because we are constructing this store directly, we can do some more interesting things. We can say that at address 1 we don't have a number, we have a box v, and in fact it's the box allocated at address 1. This means that actually at address 1 is a box that points right back to itself, and x is that box. So every time we unbox x, we're just going to get the same box back. We never get to a number. In fact, because x points to itself, we can unbox as many times as we want, and we'll still get the same box. Every time we look in that box, we just get the box itself. Now we could set up a store that has a cyclic box like that by writing a lot more of a curly program that does a let to make a box and then uses set box to put the box inside of itself. But it's neat that we can jump into the middle of a computation and set up a custom environment and store to test one particular aspect of our interpreter.